So guys, right now we're going to talk about a really cool subject called relativity. And it might go against some of the intuition that you've gained learning about Newton's laws, etc. But even though it might be a little bit confusing, if it's something that's practiced over, a bit of time just by exposure, you're going to learn it pretty good. So first thing I wanted to talk about was just reference frames. So say I'm in a truck and I'm driving 50 miles an hour and I've got a sack of oranges that I'm throwing at someone on the side of the road. If I'm doing that, whenever I throw the oranges, say I throw them with a force that speeds it up to 15 miles an hour, I'm going to see that orange moving 15 miles an hour. If someone's on the side of the road and they see a truck going 50 miles an hour and me inside of the truck throwing oranges going 15 miles an hour, they're going to see those oranges flying 65 miles an hour towards them, right? So that's fine. I mean, that's kind of intuitive. But what happens if I get back in that truck and I shine a light at them? So if I have a laser pointer and I shine it on someone at the side of the road, and let's say I drive that truck, 100 miles an hour. If I shine a laser pointer at them, that light's going to hit them at the speed of light. Now the speed of light, we might conceptualize it as something that's just really, really, really fast. It actually is a number. It has a specified limit. So it's like what we call the speed limit of the universe. So light, we usually write it down as the letter C, and it's about equal to 3 e to the 8th meters per second. So that's about how fast it is. And I'll tell you right now, there's nothing else that can go as fast as that. And light, it's never going to speed up faster than that in any situation, not in a vacuum, not in outer space or anything. So if I'm in a truck and I'm shining that light at someone, it's going to go exactly 3 e to the 8th meters per second towards them. Not the speed of light plus 100 miles an hour, even though I'm in a truck. If I'm driving away from them and I shine that light at them as I'm moving away, that light's not going to hit them kind of like the oranges. It's going to hit them the speed of light, not the speed of light minus the speed of the truck. So the speed of light, something we learn about it that's kind of weird, it's a constant. It doesn't change. It's not going to change regardless of what reference frame you're in. If I'm driving half the speed of light and light's passing me on the side, I'm not going to see it kind of moving slow. I'm going to see it just go still the speed of light. So that's constant in every reference frame. And that kind of opens the door for some weird things that go on. So to kind of, I guess, put them all in a box, the first thing you guys need to know is that C is a constant. And because of this, the weird things that happen are that first, you get short. Short as in your length is actually going to contract. You're going to get shorter. If I had a ruler and I threw it 3/4 the speed of light, it would measure shorter than what the original ruler was. Second thing, it's going to get fat. When I say fat, I mean its mass is going to increase. Now we just talked about getting shorter. It doesn't mean it's going to get fat as in it's going to grow. I mean its mass is going to increase. And the last thing, it's going to go slow. When I say it's going to go slow, I don't mean it's traveling slow. We just said it's going like 3/4 of the freaking speed of light. I mean its clock is actually going to tick a little bit slower. So if I have a watch and I'm traveling like 3/4 the speed of light, if you're watching me, you would say, wow, Spencer's clock is ticking slower than my clock. He's aging actually slower than I am. So there's some weird things that go on whenever you're going close to the speed of light. Now, an important thing to remember about all this is this stuff, I'm not going to see that happen to me if I'm the one that's moving. I'm actually never going to see this stuff happen to me, really. I'm going to see that happening to someone that I observe to be moving. Now, in order to kind of put this into an example, I know this is kind of difficult. Einstein actually was the one who came up with this. This is what we call the light clock experiment. And it's not a real experiment. It's what he called a Gedenkage, or in other words, a thought experiment. So say we have two mirrors that are facing each other. And we have a photon, or in other words, a particle of light, that's bouncing up and down against those mirrors. If it's doing that, let's say it ticks every time it hits one of the sides of the mirrors. So it's going to tick just bing, bing, bing every time it hits. And it's got a certain distance that it's covering, and it's got a certain speed that it has. Now that speed, that's not going to change whether this clock is moving or stationary. So let's draw this kind of as if it were a comic strip. A couple of other clocks, or I guess one clock that's just moving. And let's say this clock is moving close to the speed of light. Now notice I always say close to the speed of light because nothing's ever going to go the speed of light unless it's light, and nothing's ever going to go faster than the speed of light, period. So it's going close to the speed of light. Now whenever that happens, if it's moving this way really, really, really fast, that photon, that little particle of light, it's now got to travel a different distance. So it's not going to travel just straight up and down. It's got to travel now a hypotenuse. Now that's kind of interesting because say we're actually keeping track of this clock, we hear those ticks. If it's traveling a longer distance, it's not going to speed up to make sure those ticks happen at the same time that they were. It's actually going to take longer to reach each side of the clock. So if we're measuring time in this way, we see time's going to slow down. And that's just because the speed of light, it's a constant, it doesn't change. So if the speed of light doesn't change, this distance, we know it's shorter than this distance. So those ticks are actually going to be quite a bit slower the faster you move, because you have a bigger hypotenuse that you have to travel, a bigger distance that the light has to travel in order to make those ticks. Now, another thing, and this is kind of where the term relativity comes in. What if I'm sitting on the clock? What if I'm riding with it? If I'm riding with that clock, I don't see the clock moving at all. It's kind of like me right now, I'm standing on the Earth. The Earth is rotating, the Earth is orbiting around the sun might be doing whatever it is in the galaxy's doing whatever it is, but I don't know any of that. I'm in my own reference frame, and to me, Earth's not moving because I'm on the Earth, I'm with it. So say I'm on the clock, I don't know that clock's moving. And to me, that light is just going to go up and down in a straight path. To me, if I'm on the clock, it's not going to be traveling any diagonal path. While if I'm on the ground, and let's say I'm watching my friend that's sitting on the clock, if I'm watching him and that clock is moving 3/4 the speed of light, I'm going to say, wow, that clock is ticking a lot slower than my light clock here on Earth. And that's because I don't see my clock moving. I see his clock moving. I see his light that has to travel a hypotenuse. If he's on the clock, he's not going to say anything about his, but he's going to see everything else around him traveling 3/4 the speed of light. So that explains a little bit about this third point that I made, slow, or time dilation, that's what we should actually call it. So this kind of explains why we see clocks to slow down. Now the reason for other things getting fat or other things getting short, don't worry so much about why, just know that things do get fat and things do get short as they travel close to the speed of light. So say I'm on a school bus and I'm going really, really close to the speed of light, someone would look at that and they would say, wow, that's a short bus. While me being on the bus, I'm going to say, no, this bus is fine. That person's really short because I'm going to see them moving and myself is stationary. So all of these things, we only see it in other people that we perceive to be moving. So in our own reference frame, none of this happens. Now what this allows for is other weird things to happen. So say I'm in one reference frame and I'm moving 3/4 the speed of light, but I'm the one that's moving. I don't really see my cart or spaceship, whatever I'm in. I don't see it as moving. So I see none of this happening. Now if I see two flashes of light that happen at the same exact time, if we have an observer, someone that's watching my little spaceship or whatever, they're going to see those two flashes of light, but they might not see them at the same time. I might see them simultaneously. But if you think about that, maybe my length is contracted, so the light reaches me at a specific time. My time is going to be dilated relative to them, so I might hear those flashes of light at different times relative to the observer. While the observer, if they're watching that spaceship, they might see those lights flash at different periods of time. So this opens the door for what we call the Law of Simultaneity. And in words, what that says is just whenever we see things that are simultaneous in one frame of reference, it's not necessarily going to be simultaneous in another person's frame of reference. Okay? Now the main trick to be able to answer questions that have to do with relativity, you just got to make sure you know what frame of reference you're in. Are you observing someone that's moving close to the speed of light? Or are you the one that's being observed? Or are you trying to observe yourself? So answer to those questions. If you're observing someone else that's moving, you're going to see weird things happen to them. If you're observing yourself, you're probably not going to see yourself moving. Because whatever you're observing, like me on this earth in this room, me in a spaceship, I'm not going to see myself as the one that's moving. I'm going to see everything else as the thing that's moving. So me, I'm not going to see these things happen to me. I'm going to see these things happen to the people that seem to be passing by in the opposite direction.